Good evening. Our second lecture video on the electrochemistry unit will be looking at calculating the Ecell for non-standard conditions. In this video, we'll focus on looking at the relationship between the standard Gibbs free energy change and show that it is proportional to the negative of the cell potential for a redox reaction from which it is constructed. The cell with a positive Ecell will involve a thermodynamically favorable reaction, and a cell with a negative E value will have a thermodynamically unfavored reaction. We'll look in a real system under non-standard conditions. We'll be able to calculate the cell potential with varying concentrations of the different components of the cell. And the cell potential is the driving force towards the equilibrium. So we'll look at the relationship with the equilibrium for a particular cell. And then finally, we will look at the concentration cells where we have the same substance in both compartments. However, we have different concentrations. So again, we're looking more at like a Le Chatelier's principle kind of situation to see how the reaction will move to establish equilibrium. So let's begin by looking at a couple of examples to determine spontaneity. If you recall from our first video, if we have a reaction that produces a positive Ecell value, then we will have a spontaneous reaction or a thermodynamically favored reaction. If we have a negative Ecell, then that would mean that we would have a thermodynamically unfavorable reaction, and it would not happen on its own. It would have to have some type of outside power source that would be required to make the cell work, and that is your definition of an electrolytic cell, which we'll cover on our third video. So as we look at the first example here, you'll notice we have copper plus the hydrogen ions forming the Cu2 plus ion and hydrogen gas. The hydrogen ions going to hydrogen gas, that's what we use as our standard. So it's defined as a value of 0 for that standard reduction potential. The one nice thing here is we don't have to do any of the determination of whether or not the substance is undergoing the oxidation or the reduction process. It's already telling us in the problem. So if we look at our first example where we have the Cu as a solid going to the Cu2 plus, you can see here, in order to get my charge to balance, I'd have to add 2 electrons to the product side. And so that means that this is automatically undergoing the oxidation for this particular reaction. And so my reduction in this case would be the 2 H plus ions. I would add 2 electrons, and it would go to the H2. Now, you'll notice in this case, again, I've got 2 electrons here, 2 electrons here, so they would already cancel out. Don't have to do anything with any other coefficients. So in this particular case, we have our standard reduction potentials. So for the copper, I'm going to take its value, which we can see here is a positive 0.34, but that's for the reduction, not for the oxidation. So by switching the process, remember we switched the sign. So my Ecell for the copper being oxidized would be a negative 0.34 volts. And then for the hydrogen, I have it defined as a 0. So whether it's going forward or reverse, I would still have a 0. Remember, by switching the sign for the reaction, all you have to do at that point is just simply add your 2 Ecell values together, and that would give me a negative 0.34 volts. So that means that my first reaction would not be spontaneous or thermodynamically favorable at that particular situation. So now I can look at my second example, and I have the chlorine gas going to the chloride ions, and I have the iodide ions going to iodine as a solid. So in this particular instance, my oxidation, if you would notice, would be the 2I minus going to the I2 as a solid plus 2 electrons. And then my reduction would be the chlorine adding 2 electrons and going to the chloride ions. So when I look at my values here, I have for the chlorine undergoing the reduction process a very positive 0.136. So that is a very favorable process for the Ecell to occur. And for the iodine to go to the iodide ion, it's a positive 0.54. However, again, we're trying to force it to go in the opposite direction and go from the iodide ions back to the iodine as a solid. So I would flip my value for Ecell in this case and have a negative 0.54 coming from that positive 0.54 for the opposite process. And now I can simply add these two together, and 1.36 minus 0.54, that should give me a positive 0.82 volts. So as a result, this second process would be thermodynamically favorable. We're now going to focus our relationship between free energy and electrical work. When we look at the delta G value, we know that it is proportional to the negative Ecell for a particular system. We also related delta G as the amount of work that can be done maximum on these surroundings by the system. And so we can say that the negative Ecell for a particular reaction is equal to the negative W max divided by its charge. The charge by definition is the number of moles of electrons times Faraday's constant, which is just basically the charge per mole of electrons. So that way you can get it into just your charge. And the value for that Faraday's constant has been experimentally found to be 96,485 coulombs per mole of electrons. By definition, 1 volt is equal to 1 joule of energy per coulomb for charge. We can rearrange the equation in terms of coulombs and isolate the coulombs by itself, and we could say that we'd have 1 joule per 1 volt equals 1 coulomb. And so Faraday's constant can be rewritten as 96,485 or 9.65 times 10 to the fourth joules per volt times moles of electrons. With the delta G equaling the maximum amount of work, we can set that equal to the charge times the negative value for the Ecell. We've now defined the charge as being the NF, so I can substitute the NF in for the charge, and that gives me the negative N times Fe for the cell to give us the delta G value. Notice again I have a negative sign in front, so that gives us that relationship. If I have a positive value for Ecell, then I'm going to have a negative value for delta G. That would mean that I would have a thermodynamically favorable process. If my Ecell is a negative value, then that would mean that the product of negative NFE would be a positive value, and that would mean that I'd have a non-spontaneous or unthermodynamically favorable process, which means that I would then have an electrolytic cell, which we'll cover in our next video. So we can look at these relationships here. In the standard state, we know that the delta G naught is equal to negative NF Ecell, and we also can now relate this to equilibrium. The delta G naught is equal to a negative RT ln of K, and if we combine these two concepts together, we can get the Ecell and its relationship to the equilibrium constant by using negative RT divided by NF times the ln of K. Now, ln of K, not very friendly for that value, so we can convert that into logs. And if you remember, we can do that conversion with the ln going to logs by multiplying it by 2.303. And so again, the R value here, I'd have the 8.314 joules per mole Kelvin. I can multiply that times the temperature, which in the standard state would be 298 Kelvin, and then dividing that by the N and by the 96,485 joules per volt times moles of electrons, you can get everything to cancel out and give us a simplified equation for the relationship with E naught and K. So we'll talk about that more on the next slide. So as we look at the values here for your delta G, for your Ecell, and for your K, we can come up with our relationships between all of these. Between Ecell and delta G, we have the negative NFE for the cell. We have delta G and K being the negative RT ln of K, and we have the E naught for the cell and K being the relationship of negative RT ln of K divided by the NF. So as I said, we can simplify that because everything here with the R and T and the F, those are all constants. The only thing that would change would be your number of moles of electrons. This value for N here would be the value for the moles of electrons from your redox reaction. So if you remember when we were doing our redox processes, just trying to get those balanced equations set up, and I would tell you to write N off to the side, that's the N value that we're talking about. So how many moles of electrons are required to have your oxidation and your reduction reactions balanced out. So that's the only thing that won't be a constant in there. You can apply the ln going to a log using the 2.303, and that gives us a final reaction or equation for those reactions of the 0.0592 volts per N value for your moles of electrons times the log of K. So you can use this as a simplified version of solving for K from your Ecell at standard conditions. So again, when we're talking big picture, when my delta G is less than 0, negative number, that would mean that again my K value is greater than 1. Talked about that in our thermodynamics videos that we had. So again, that would tell me that I'd have a product favored reaction. So that means that the Ecell would be a value greater than 0. So I would have a thermodynamically favorable process. If delta G is equal to 0, then we said that process was at equilibrium. We'd have our K value equaling 1, and our Ecell would be 0. So for all intents and purposes here, again, that would be basically where our Q and our K are equal to each other, because remember we talked about that as basically being the relationship between Q and K for that non-standard condition type of equation. So in terms of the Ecell for this, when that value is equal to 0, when we're talking about it being at equilibrium, that just basically means that we have a dead battery. So that's when it's time to replace. And finally, if I have a delta G not being greater than 0, then my K would be less than 1 because I would have a reactant favored process, and my Ecell would be less than 1. I'd have a negative value, so in order to get that battery to work, that would have to be an electrolytic cell. So let's look at an example problem here for calculating K and delta G from our Ecell value. So we have lead can displace silver from solution. Pb as a solid plus 2Ag plus forms Pb2 plus and 2Ag as a solid. So the first thing that we need to do is set up our half reactions. So I have Pb 2 plus 2 electrons forms Pb as a solid. The Ecell value for that is negative 0.13, and I have Ag plus E minus forms Ag as a solid, and the Ecell for that is 0.8. So in this particular instance, we do need to decide which one is going to undergo reduction and which one is going to undergo oxidation. So again, we want to look at our Ecell values, and because the silver ion going to the silver as a solid has a positive reduction potential, and the lead going to the lead as a solid has a negative potential, we know that the silver is therefore going to be undergoing the reduction and the lead is going to undergo oxidation. So as a result, when we flip this reaction, we will change the sign and we'll flip that times a -1. I'd have to multiply this reaction by 2 to have it equal out for my number of electrons. So remember though, that does not change the value for the Ecell. That is an intensive property, so it is not dependent on the amount of matter that's present. So I would have 0.93 volts for my electrochemical cell voltage. So now, or potential difference, when I now look at this, I'm going to go ahead and solve for the delta G naught, and that would be equal to negative NF Ecell for my particular reaction. So as I go through this process, I would have my delta G being equal to a -2, because again here my N would equal 2. and then I'd multiply that times the F. I'm going to go ahead and convert that straight into kilojoules because I need that for the delta G. So I'd have 96,485 turning into 96.485, and that's kilojoules per volt times moles of electrons. The 2 is your number of moles of electrons, so they would cancel, and then I would multiply that times the Ecell value, which was a positive 0.93 volts. So my volts now canceled too, and I'm left with kilojoules. So my delta G for this overall reaction would be negative 179.5 kilojoules per mole of reaction. So I've got that overall. Now, as I move on to the next part, calculating the value for K. So we can do this one of two ways. We can either take the value for delta G that we have just calculated and use the negative RT ln of K. So if I were to do that, I could have the negative 8.314 multiplied by the 298 and multiplied by the ln of K. So to solve for K, I would take the E and raise it to the negative delta G over RT. So when I do that, I'd have a negative for the negative 179.5, so that would be a positive. I'm going to go ahead and convert that into joules, 179,500, and I'm going to divide that by the 8.314 and the 298. So when we do that, we end up with our K value being approximately 2.9 times 10 to the positive 31st power. So I'd have it using that method. I could also get the same answer using the equation that we had, 0.0592 over n times the log of K equals the Ecell for the particular reaction. So if I do this now, I could take the Ecell, multiply it by the value for n, divide it by the 0.0592. It's a little bit of debate depending on which textbook or source you're using. You might see it as 0.0592, you might see it as 0.0591. So our answer is going to be slightly off, but you'll see relatively the same magnitude with this, depending on which value that you use. And then that would be equal to the log of K. So I could take all of this, raise 10 to that power to have it equal K. So if I took 10 times the 0.9 or 10 raised to the 0.93 volts times the 2 for a value for n and divide that by the 0.0592, that ends up giving me a value for 10 of 10 being raised to the 31.47, which would equal 2.96 times 10 to the 31st. So really close. 2.9 is like 2.87 versus 2.96, but both are raised to the 31st power. And with something that large, that small little bit of difference doesn't make any difference overall for your final answer. So 2.96 times 10 to the 31st for either value. Very, very favorable process. All right, so let's look at one more example problem and try to combine a couple of different relationships that we would have. So for part A, we want to calculate the delta G, the K, and the Ecell for the following reaction. And then for part B, whatever we had for part A, we want to see what the values for delta E, or for E naught, delta G, and K would be when the reaction is written as 2Ag plus 1/2 O2 plus 2H plus forms 2Ag plus and H2O. So starting off with the part A for this particular reaction. So the first thing we need to do is determine our Ecell. So if you notice, I have the half reaction 4Ag as a solid going to 4Ag plus. So when I come over here to my chart dealing with Ag, I have the reduction, Ag plus the electron forms Ag as a solid, being a positive 0.8 volts. So if I'm rewriting that the other way, where I have the 4Ag as a solid, and we are going to the Ag plus 4 electrons, that Ecell value then as we flip the direction, would now be a negative 0.80 volts. The oxygen, going to add the 4 H pluses plus the 4 electrons, forming 2 waters. That Ecell value, and we have to be careful because I have an O2 right here, but notice that's producing OH minus, so that's not the one that I want to use. I want to go up here. I have a second one dealing with oxygen plus the 4 hydrogen ions plus the 4 electrons, forming 2 waters. That's the proper reaction, and it's a positive 1.23 volts. So if I add those two together, I have a positive 0.43 volts. So to solve for the delta G, again, I'm taking the negative for the N, which in this case, my N was 4, because I have 4 electrons here, 4 electrons there. So I have a negative 4 times the Faraday's constant, 96.485 kilojoules per volts times moles of electrons. And finally, the Ecell value, a positive 0.43 volts. So my delta G for this particular reaction would be a negative 166 kilojoules per mole. When I would look at that value, calculating out the Ecell for, or the K for that particular reaction, again, I'm going to do the 10 raised to the Ecell multiplied by my value for N divided by 0.0592. So I have 0.43 volts times 4 divided by the 0.0592. And when we do that, that equals 29.05. So if I raise 10 to the 29.05, I end up with 1.25 times 10 to the 29th power. So again, very favorable process for this to take place. If we now look at the other part of this, where we can take the values and manipulate the equations, remember for our delta G equations, we would take whatever we do with the coefficients, and we would do the same thing with our values for the particular delta G value. So in this case, if you notice, I'm dividing it by 2. So for my part B, I would take the 166 kilojoules per mole, and I would divide it by 2 to equal my new delta G for that particular reaction. So I'd have 83 kilojoules per mole. And why I like this problem, it gives you the ability to think about all those things, equilibrium, that we've talked about for so long. And if you remember, for your equilibrium reactions, if we change the coefficients, we would raise K to that particular power. So since I am dividing it by 2, I can take my value for K and take the square root of it. And if I take the square root of K, I end up with 3.5 times 10 to the 14th power. So that would be my new value for K. So now here's where we're going to get into the non-standard conditions. So for your non-standard conditions for your Ecells, we use something that we call the Nernst equation. So from our work with the Gibbs free energy, we remember that the non-standard conditions, the delta G is equal to the delta G naught plus the RT for the ln of Q. We can set that equal to the negative NFE and the negative NFE naught for each of our delta G's plus the RT ln of Q. And when we do that, we can rearrange our equation to give us a little bit more easily usable version of that. And when we look at the Nernst equation, we can simplify this down to being the E equals the Ecell minus 0.0592 over N times the log of Q. Again, doing the same thing using the conversion between ln and the log with the 2.303, the product of the RT and the 2.303, giving us the 0.0592, and we can divide that by the value for n. So we have this as our overall equation that we can use for the Nernst equation to determine how the Ecell is going to compare to the E naught for the cell under the non-standard conditions. So the same type of thing applies. If I have a positive value for Q, again, that is larger than 1 for that value of Q, then I'm going to be subtracting off a value from the E naught, and that means that the E would be a less positive or a more negative number. Okay, so let's go ahead and put all of our relationships together. So the first thing that we had was the delta G equals the delta G naught plus the RT ln of Q. We had the negative NF Ecell equals a negative NF Ecell, and that should be a naught value here, plus the RT ln of Q. And we could then simplify it down to the Ecell equals the E naught for the cell minus RT divided by NF times the ln of Q. So again, you can change that relationship out to give us that simplified version like we had talked about. When we have our Q value being less than 1, and thus we have a reactant being greater than the products, we would know that the ln for the Q would be less than 0, and we would have the Ecell being greater than the E naught, because I'd be subtracting a negative. When we have the Q equaling 1, and thus the reactant and product concentrations are equal, ln of Q would equal 0, so I'd have the Ecell equaling the E naught for the cell. And finally, if Q is greater than 1, and thus our reactant concentration is less than the product concentration, the ln of Q would be greater than 0, so my Ecell would be less than my E naught. So thinking along those lines, if the Q is greater than 1, we're using 1 as our baseline in this case for the relationship between the reactants and products. So when we're looking at that, if the Q value is greater than 1, then we know it's going to shift back in the reverse direction. So I'd have a less favorable process taking place, and my Ecell would become smaller. If my Q is less than 1, then I know that I would have a number that I'd be subtracting that would be a negative value, and so my Ecell would be larger than the E naught for the particular reaction. So let's go ahead and look at a couple of graphs and some example problems here to wrap up this video. So what we can look at here in this particular instance is the effect of the change in concentrations for a particular cell on the overall cell potential for a particular system. So we're going to look at the relationship between the copper and zinc cell. In this particular instance, if you recall, which is okay if you don't, zinc is a more active metal than the copper is, so I know it's going to undergo the oxidation process more readily than the copper will. So I'd have the Zn as a solid reacting with the Cu2+, and it would form Zn2+ and the Cu as a solid. So as I'm looking at this reaction, setting up my equilibrium expression, I would have my Q in this case. Notice again, because they are each 2+ going to 0 or 0 going to 2+, I would have a 1 for all of my coefficients here to balance out my redox reaction. So make sure again that you balance out your equation to get your proper coefficients and powers for Q. So I'd have in this the products of reactants Zn2+, which would be aqueous, and we would put that over the copper 2+, which would be aqueous as well. So I'd have this as my relationship. So again, as I look at this here, you can see that when my Q is less than 1, again, you can have your Q values along the bottom here. As my Q is less than 1, you can see that my cell potential increases, because again, as the Q is less than 1, that would mean that I would have more reactants than products. And so to achieve equilibrium, the reaction would have to shift to the right. Shifting to the right, I'd have the larger value for the E naught because I'd be subtracting a negative value from the Ecell. So I would have, in that case, a larger Ecell for a particular system. As I look at the opposite, where my Q is now greater than 1, I have too much zinc compared to the copper, and so my Q value is larger than 1. Again, taking the negative RT ln of Q, that would give me a overall negative value that I'd be subtracting from that positive Ecell. So my Ecell for the overall reaction would become less. So you always want to be looking at those types of situations, and you can give just a qualitative standpoint of how the cell potential will be different at that particular concentration compared to what it would be under standard conditions. All right, so now let's look at a couple of example problems to calculate the cell potential under non-standard conditions. So in our first reaction here, we have the dichromate ion reacting with the iodide ion to produce the chromium 3+ ion and the iodine as a solid. So they tell us that the dichromate ion concentration is 2 molar, the H+ concentration 1 molar, I- is 1 molar, and the Cr3+ is also 1.0 times 10 to the minus 5th molar. So we need to figure out our Ecell first. So for the part A, the first part here, the Cr2O7 2- plus the 14H+ plus 6 electrons forming the 2 Cr3+ and 7 H2Os. That Ecell for that particular reaction is equal to a positive 1.33 volts. And we had this previously, the 6I- going to the 3I2 plus the 6 electrons. Again, just getting in good habits, I know that my N is equal to 6 here, and that Ecell for this particular reaction, because we're flipping it, it was originally positive 0.54, so now it will become a negative 0.54 volts, and so that would give me the overall Ecell for that particular reaction being a positive 0.79 volts. So at this point, I can now solve for Q, so I'm going to set up my Q value, and that would be equal to the Cr3+ concentration squared divided by the Cr2O7 2- concentration times H+ to the 14th and I- raised to the 6th power. So each of these being 1, those will essentially cancel off. So I have, in this particular instance, 1 times 10 to the minus 5th squared divided by 2, equaling my value for Q. So my Q ends up being 5 times 10 to the negative 11th power. So to solve for the cell, the Ecell for this particular reaction, I would have the E naught for the cell minus the 0.0592 divided by N times the log of Q. So I have the Ecell equaling 0.79 volts minus 0.0592 divided by 6 times the log of 5 times 10 to the minus 11th. And my value for the Ecell will become, let's see, 0.79. We have a negative 0.102, so I'd have a 0.9892 volts for the final cell potential. This part right here, taking the 0.0592 divided by 6 times the log of 5 times 10 to the minus 11th, that equals a negative 0.102, so 0.79 minus a negative 0.102 gives us 0.892 volts for this particular reaction. So if I do the same thing with my second reaction, I have the Pb2+ going to Pb as a solid. So the setting up these half reactions, I have the reduction Pb2+ plus 2 electrons forming the Pb as a solid. I had the Zn as a solid going to Zn2+ plus 2 electrons. The Ecell we had for this reaction, again, I'm just looking these values up off of the table. We had this in a previous problem, and it was negative 0.13 volts for the reduction of the lead. And the zinc, the reduction was a negative 0.576. So because I'm now flipping it, because it's the more negative value, I'm going to change that to a positive 0.76 volts for the oxidation, and that will give us a total Ecell of 0.63. They gave us the concentrations for the lead being 1.5 times 10 to the minus third, and the zinc as the 0.55. You'll notice that the zinc ion is what's in the numerator, so I'd have the Zn2 plus divided by the Pb2 plus for the denominator, so 0.55 divided by 1.5 times 10 to the minus third gives me a Q value. Let's see what we have for that. We have 0.55 divided by 0.0015, and that gives us 367 for the value of Q. So if I take the 0.0592 and I divide that by 2, and then multiply that times the log of 367, that equals 0.0759. So I can now notice that as a positive. So I could take the 0.63 volts minus the 0.0759 for that value, and I get 0.554 volts for my overall reaction. So notice in this case, Q is greater than 1, so my cell potential became smaller than the E naught. Still thermodynamically favored, but just not as much. So I would not get as much voltage out of that cell compared to the other. Okay, so the last thing that we're going to talk about on this video is just simply a concentration cell. So when we have a concentration cell, this is something where we're just utilizing a difference in concentrations of this same substance to produce an electrical current by trying to balance out the charges within the two different compartments. So you'll notice in both of these compartments I have a AgNO3 solution. However, in the one on the left I have a 0.1 molar solution, and in the second I have a 1 molar solution. So we're going to try to equalize the concentrations in each of the different compartments. So you'll notice with my electrode, we can assume, because you can tell in the picture that this one is basically eroding away the metal, you can tell that this would represent the anode because it's losing mass. And then this one here, you can see all the little bits of silver that are starting to plate onto this electrode. So it's gaining mass, and therefore we can assume that it is the cathode. So when that happens, in order to plate the silver, we're going to lower the concentration of the Ag plus ions in the solution. And here, because it's eroding away the metal, we're assuming that we're increasing the concentration of the Ag plus ions in the solution. That is going to provide a surplus of electrons in this electrode, and so it's going to force the electrons to move from the left compartment to the right compartment. These cells, they can create a battery. However, the voltages for these types of conditions, because again you have each of the compartment having the same electrical potential initially, you're going to have a very small change in voltage that would occur. So you might get a 1/10 of a volt out of it, maybe, more often than not less than that, but you will at least be able to get a small amount of current to come from these different cells. So that wraps up the second video for us here. Trying to keep it as low as I can for the time. The last video that we will talk about will be covering your electrolytic cells. And we'll talk about the stoichiometry of the electrolytic process for electroplating or for removing a certain type of metal from an ore or a mixture of metals. So that wraps this one up. There'll be some practice problems for you guys to work on for these non-standard conditions, and I will see you in class tomorrow. Hopefully you'll have some questions for me. Have a good night.